For Chapter 17, Reassessment, I used the concept from Homework 3 on WebAssign. I have a thin rod with length L and uniform force Q. For this problem, I want to find the potential difference from A to B and from A to C. First, I determine the origin to be at the center of the rod and the points A and B to be along the positive x-axis. To determine the potential difference from A to B, I use the electric field equation of a rod where R is smaller than L. In this case, R in the equation is actually represented by x, and by looking at this equation, I am able to realize that the magnitude of the electric field decreases from A to B. Therefore, I need to set up an integral to find dx. I can use the potential difference equation, but first I need to relate dl with dx. At the origin of my determined xy plane, a small piece of the rod is constant in all variables except the x component. Therefore, this means that E.dl actually equals the x component of E times dx. Now I can plug this information along with my electric field equation into the integral and solve from the limits of the x component of A to the x component of B. For my equation, I found that the potential difference from A to B equals the negative constant times 2q over L times the difference between the natural log of the x component of B minus the natural log of the x component of A. I can distribute this negative sign to the parentheses and find that the order of these two components switch. By using previous knowledge, I can again simplify the equation because I know that the difference in the natural logs equals the log of the ratio of those quantities. With this simplified version, I could plug my values and find the potential difference from A to B, which in this situation equals negative 19,775 volts. To calculate the potential difference from A to C, the path is independent, but since I already have found the potential difference from A to B, I can find delta V from B to C and add the values together for the total change from A to C. In this problem, relative to L, B and C are very close, so I'm assuming that the electric field at C equals the electric field at B. Since I already know the first part of this equation, all I need to find is the second component. With looking at this diagram, it is easy to see that the electric field vector, which is the purple vector, is perpendicular to the dl vector, which is the light blue vector. Because E.dl is perpendicular, the value of E.dl equals 0, and therefore the potential difference from B to C also equals 0. So to find BC minus BA, I found the sum of the first component, which is negative 1.98 times 10 to the 4th volts, plus the second component, which is 0, to equal negative 1.98 times 10 to the 4th volts. And this is the total change in potential from A to C.